So you have that first part, but then if you compound the interest more than one time a year, that's where this numerator, this exponent is coming from. Again, where your n is the number of compoundings per year. So again, the initial amount deposited was our P. The interest rate in decimal form, we're calling it R. The number of compounds per year is our N. Okay. So for example, we have this case. It says the balance for a deposit of $1,000 at 8% at various compounding periods are shown in the table below. So on the left side, we have the number of compoundings per year, and on the right, we have our balance after the compound. So say you only compound the interest one time of the year, once a year. We call it annually. So then it said for a balance, the balance for a deposit where your P is 1,000, with your rate 8%. That's where the 8.8 comes from. And if it's done where your N is 1, is compounded one time a year, this calculation produces this number. If it's compounded twice a year, so with your initial deposit at 1,000 done twice a year at 8%, is this amount. If it's done quarterly, that means you do it 4 times a year. It's given by this formula. If it's done monthly, that means you compound the interest 12 times a year. It's given by this formula. If it's done daily, that means you do it 365 days out of the year. It's given by this formula. If you notice that as n increases, the balance of A is approaching a limit. So let's take a look at this. We're going to let x be r over n. So now as n goes to infinity, with that fixed r, x gets closer and closer to 0. That's like when we had the discussion of 1 over infinity, or something over infinity, or finite over infinity. That term gets closer and closer to 0. So as n goes to infinity, x goes to 0. So if we want to look at the limit of our function here, where a is p times this, we want to see how does this function behave as n goes to infinity. So a is going to be the limit as n goes to infinity of our original function. But this function here is going to be the same as this line. We want this n over r. So we divided this by r and multiplied by r. So we can get this n over r. We're just doing a manipulation so we can use that definition of E. So then if x is r over n, then 1 over x is going to be n over r. So that's, you have an n over r here. So then this r over n is x. So this r over n is x. N over r is 1 over x. So n over r is 1 over x. Your initial amount P does not depend on n or x. It doesn't depend on n. And this outside r also does not depend on n. So we can pass the limit to the inside of the function. And so here again, your P doesn't depend on x, your R doesn't depend on x, so you can pass the limit to the inside. And again, we said that as n goes to infinity, x goes to 0. So here, your x goes to 0. So now, this inside part here is nothing but our definition for E. So then this is really just P times e to the power of r. Okay. So what this limit is telling us, it says the limit is the balance after 1 year of continuous compounding. So for a deposit of $1,000 at 8% compounded continuously, the balance at the end of the year would be the $1,083.29. So with this notion of compounding interest, we're saying that even if you were to take the interest each and every day on an account, the most is bounded, or there's an actual limit to it. You know, it's not gonna just keep going to infinity. There's a certain amount that you could do in a given year. Okay. So just a recap on compound interest. So if P is the amount that you're going to deposit, T is your number of years, A is the balance after you do your compound, and R is going to be the annual interest rate in decimal form. Then if it's compounded in times per year, we're going to use this formula that we discovered. Again, where your T is going to be your number of years. Again, your P is your initial deposit. Your R is your annual interest rate. Your N is going to be the number of times the interest is compounded per year. Your T is going to be the number of years that this applies to. And then if it's compounded continuously, your amount is going to be your initial deposit times E to the power of your rate times the number of years. Okay. So if we look at example 2 on finding account balances. Let me see. In this example, you're creating a trust fund for your newborn nephew. You deposit $12,000 in an account with the instructions that the account be turned over to your nephew on his 25th birthday. Compare the balances in the account for each situation. Which account should you use? Now, on you guys' paper, I left this part off. This is the part I was like, we're missing something. So this is the rest of the question that I didn't give you. For part A, let me see. We want to find the amount when the rate is 7% compounded continuously. B, find the amount when the rate is 7% compounded quarterly. Again, quarterly, how many quarters in a year? 4. So you know your N is going to be 4 there. And then for C, we want 11% compounded continuously, and D, 11% compounded quarterly. So for A, if we're doing 7% compounded continuously, we use that second equation that we just gave. So it's just going to be your P times E to the power of RT. So your P, your initial deposit was $12,000. Your rate is 7%. So that's where the 0.07 comes from. And it says 25 years from now. He was is your newborn baby nephew on his 25th birthday. So that's 25 years from now. So then if you calculate that, you get approximately this. So with an initial deposit of $12,000 at a rate of 7% after 25 years compounded continuously, the amount would be the $69,000 you see here. With part B, if it's 7% compounded quarterly, again with an initial deposit of $12,000 at a rate of 7% compounded 4 times a year, done 25 years, you're going to get $68,000. Okay. For C, if you do an initial deposit of $12,000 at a rate of 11% for 25 years compounded continuously, you're going to get $187,000 approximately. But if you do an initial deposit of $12,000 at a rate of 11% compounded 4 times a year, in other words, compounded quarterly, if you do that for 25 years, it's going to be $180,000. So these are your options for your accounts for A, B, C, and D. You have these different accounts to choose from. It says, which account would you choose? Well, obviously, you're going to choose the account that gives you the greater yield after that time. So that's part C. If you look at C, you see with that account, after that amount of time, it would have the greatest yield. So we would use part C. Let me see. The growth of the accounts for part A and C are shown in the figure. So let's see. The top line here is for part C. The bottom line here is for part A. Yeah. So again, we would choose the account described in part C because it earns more money than the other accounts. Okay. So in the previous discussion,